Good morning, everyone. This is January 2021, Unit 6 of IEL Chemistry. I will go through this paper. If you want this paper or the marking scheme, you can leave your ID in our comment box. The first question, a student carried out some tests on four aqueous solutions A, B, C, and D. One of the solution is barium chloride. The student is asked to add A to sample B, C, and D. A separate test tube. A container A, a solution has a hazard label. So what does it mean? This is a sign normally used for acids which are corrosive. So this label, what does this label shows? It shows it is corrosive. Describe how would you add a small quantity. So corrosive liquid, normally we use a dropper or a teat pipette, and we add drop by drop. B is a blue solution. When A is added to B, solution first turn green and then gradually yellow. So this blue solution give you an idea that there is a copper ion. And why it was blue? Because it's a complex of the copper, the aqua complex of copper. That's why it is blue. But when we are adding an acid, it is turning green and then it turn into yellow. It means that there is a ligand exchange. It turned into complex of copper which is having chloride ions as a ligand. So give a formula of the cation. The cation, you can write copper 2 or you can write the complex, because this hole is also responsible for this blue color. What is a neutral ligand? So overall complex will have the charge same as due to copper. You don't have to write plus 2 here, just I was using it to explain the idea. When A is added to C, a vigorous effervescence occurs. So this confirms that maybe a carbonate or hydrogen carbonate is there. Identify by name or formula the gas which is produced, the carbon dioxide gas, and name or formula the anions. It might have carbonate or hydrogen carbonate, because these two ions are responsible for releasing carbon dioxide when acid is added. And A, we identify it as an acid, and because it was forming a yellow solution as it was added to blue solution B, then it was first turned green and then turned yellow. It shows that it is a chloride, because chloride precipitate of copper are yellow in color. Identify A by name or formula and justify your answer. So how we can justify that what is A? So we can say A was copper ion was there, and then originally the copper ion, when we add the solution A, and it is acid we identify because it was giving phase effervescence with carbonate, so proton is there, and this, when we added to copper solution, it was turning into yellow. It shows that the tetrachlorocuprate is formed. That's why it was turning. So identity of A, it is acid, HCl, and because yellow solution formed with copper complex. Then A is added to D, no change is seen. A small amount of this mixture was added to B, a white PPT. Suggests what can be deduced about solution B and D. So what we can say about solution B, if it is a first when it was added to D, we did not observe anything. But when it is added to small amount of this mixture was added to B and white PPT is there. So why there's a, and they already mentioned in the beginning of the question that one of them is barium chloride. So barium chloride, and when barium chloride, barium ion mixed with sulfate ion, it will give barium sulfate. So it shows, because with when it is added to solution, it was giving precipitates. So A was, we already identify HCl, and when it is added to D, it does not give any change. But what else? Because we are left with two options: either this will be barium chloride, B will be D will be barium chloride, or B will be barium chloride. But when we add them, we do not observe anything, no visible change. But when small quantity of B, so it means this substance suggests what can be deduced about the solution B and D. So when a small mixture is added, a small amount of this mixture is added to B, this is giving white precipitate. It means the white precipitate are due to barium sulfate. So what ion is present in this solution? It contains a sulfate ion, and in the beginning we identified that it was having copper as well. So this confirms that this is copper sulfate. And what about solution D? So solution D will be barium chloride. So basically what happened when HCl is mixed with barium chloride, there is no visible change, no observation. And then barium chloride is added to copper sulfate. So it will form barium sulfate, and that result in a white precipitates. Concentrated solution of ammonia is added to be initially blue precipitate. When more is added, so what will happen? There will be a Ligand exchange. The precipitate dissolve dark blue. We have to write the formula for this blue color solution. So first it was complex with water, but then when we add, there's an acid base reaction, protons are removed, so it will form copper hydroxide. That is why it is blue precipitate. Then when we add an excess, the precipitate dissolve to form a deep blue solution, and that deep blue solution is due to the Ligand exchange. So you have copper, identify blue precipitate which are formed, so copper hydroxides precipitate, copper 2 hydroxide, and water molecules are also attached as a neutral. This hole will be solid. Why this hole will be solid? Because it does not have any charge on the complex. And then when we add an excess, so it will have amine groups. Some of the water molecules are replaced by amine groups, and the complex will have a charge. That's why it will form a deep blue solution. A solution of sodium salt of EDTA, N4 and EDTA is added. So it is a polydentate, means polydentate ligand, means it can have many ways to attach to a complex. So when polydentate, the higher increase in entropy is there. So write an equation for reaction when sample of solution F, the solution turned pale blue. So if solution turned pale blue, precipitate are not formed, it means there is a charge on the complex. And how we write this reaction? So we have originally, like, this was what is formed as a solution, and we add Na4 EDTA. So this will displace all of these molecules, result in, because it's a polydentate ligand, so it will attach from many sides. and it's a soluble. And what is the valency of EDTA? We can clearly work out from the sodium is +1, so that is -4. So the charge on the complex will be -2 because -4 and +2, so charge will be -2. Plus it will release sodium ions and ammonia plus water molecules. State symbols are not required, so state symbols you don't have to write the state for each. Students, question 2, students were told to determine the concentration of solution of potassium chlorate. Two methods are used, precipitation and titration. First method is precipitation. We bubble excess of sulfur dioxide in 100 cm cube of potassium chlorate and then boil the resulting mixture to remove excess of sulfur dioxide, then add silver nitrate until no more silver chloride precipitates form. Filter and dry and brevet the equation. So first what happened, this chlorate ion is reacting with sulfur dioxide, result in a formation of chloride ion and sulfate ion. And we boil the mix to remove excess and then add silver nitrate until no more silver chloride precipitate form. Basically, silver react with chloride ion to form silver chloride. Identify the main hazard in step 1, giving a safety precaution. Look, when you have acidic or a toxic gas, so we should have a fume cupboard. The reaction in step 2 produce 0.43 grams of white PPT. Calculate the concentration. So first, using silver chloride moles, will get, like the mass of silver chloride will get the most of silver chloride, and moles of silver chloride are same as moles of chloride ion. And using a moles of chloride ion, we can find the moles of chlorate ion, and from moles of chlorate ion we have the volume. So moles divided by volume, we will get the concentration of this potassium chlorate. So moles equal mass in gram over molar mass. First we should get the moles of silver chloride, which is moles of AgCl. Mass in gram is 0.430 divided by molar mass. You will add the mass for silver and chlorine, which is 35.5. The total will be 143.4. That will give the moles of silver chloride, which is 2.99 into 10 to the power minus 3. Then when you use the ratio, 1:1 is the ratio, so same number of moles you will get for chlorate ion. And then you need a concentration, so concentration and moles of chlorate ion will be same as moles of potassium chlorate. The ratio is 1:1. So concentration of potassium chlorate, moles divided by volume. So moles are 2.99 into 10 to the power minus 3. But what about the total number of the moles? As you can see, the total number of the moles, because we have moles of chloride, like we have silver chloride, so using the ratio of silver chloride to chloride ion, the ratio is 1:1. Then chloride ion to chlorate ion, the ratio is also 1:1. And from chlorate ion to potassium chloride, that is also the ratio is 1:1. That's why what moles you will get for silver chloride, same moles you will get for potassium chlorate. And divide by volume of the solution, as I mentioned in the beginning, in 100 cm cube. So original, it will be 100 cm cube or divide by 1000, so it will be 0.1. So when we solve, this will be 2.95 into 10 to the power minus 2 moles per decimeter cube. next part, a student who used method 1 obtained a value that was significantly larger than actual concentration, suggests a possible source of experimental error which might lead to result. Basically what student did, student filter of the solution and he weighed the precipitate. So the important thing is the weighing of the precipitate. If this weight is coming out more, we'll get greater amount of chloride ion and we'll get greater amount of chlorate ion. So maybe what happened, the crystals, the precipitate might not be completely dried, or it was having a trace of solution. That is why the actual value will be higher than the value which is calculated is higher than the actual value. Titration, second method, mix a sample of potassium chlorate 5 solution with acidified solution containing iron 2. Remove the chloride ion produced and determine the concentration of excess of iron 2 ions by titration the whole solution with standard solution of potassium manganate 7. So first what we did, we reacted chlorate ion with iron 2 oxidized to iron 3 and chlorate ion changed to chloride ion. Here chlorine oxidation number is plus 5, so it is reduced to minus 1. The color change observed in step 1. So what is the color change observed in step 1? So we have iron 2, it is changing into iron 3. So if iron 2 is there, because of this iron 2 originally it should be green in color, and then it turned into iron 2 changes to iron 3, so iron 2 is green, and iron 3 it is red brown, or if it is having a lower concentration then it will be yellow brown is also the right one. Describe how to carry out titration step 3. You should identify suitable apparatus and any additional chemical we need. Step 3, what we are doing, we are to determine, we add excess of iron to iron, determine the concentration of excess of iron to iron, the whole of the solution with standard solution of potassium. So we are titrating with potassium manganate. So what we will do, we will pipette out, like example 10 cm cube of that solution, or we will take out that complete solution. We will fill the burette with potassium manganate solution, and we will titrate iron 2 solution, adding KMNO4 drop by drop, because here we don't want to mention experimental like we don't want to repeat it. That's why in the beginning we are adding drop by drop. If we want to repeat, then first we'll find you do a rough titer like a range finder, and then we'll repeat when we are closer to this volume. Then what happened, because when Mn2 is manganate ion is converting in, when the reaction is there, Mn7 change to Mn2 and an iron 2 is changing into iron 3. This is also a self indication or self indicator reaction in which we don't add an outside indicator, we, because Mn7, in when you have Mn7 in the burette, potassium manganate 7 is there, it is purple. But the moment it is reacted with iron 2, it will turn into Mn2. Iron 2 will oxidize to iron 3, and Mn2 will be there, turn into, Mn7 is there, turn into Mn2. So it will remain colorless. Once all of the iron is oxidized, then there is no more reaction. So Mn7 will be there in the solution, and solution will turn pink. So record the volume of KMnO4. Then it shows a color change from colorless to pink. And we should the improvement, we should look perpendicular, avoid parallax error, and we should swirl the mixture, and we should rinse, pure it, with KMnO4 because we are filling it with KMnO4. First we should rinse with water and then with KMnO4. These are the additional steps which you can do for this titration. In method 2, 50 cm cube of potassium chloride was mixed with 150 cm cube of 0.07 mole per dm cube of iron 2, and iron 2 sulfate is in excess. So first reaction, iron 2 sulfate is in excess, then the whole of this solution is titrated with potassium manganate. Means the remaining iron 2 is titrated with potassium manganate. Calculate the concentration of potassium chloride solution. So first what we will do, we will find the total moles of iron sulfate as we know the concentration and volume. So we'll find the total moles of iron sulfate, and we'll find the moles of iron sulfate which are unreacted. How we'll know moles of iron sulfate which are unreacted? That are the moles which are reacting with potassium manganate. And we subtract the two to get the moles of iron 2 reacted with chlorate ion, and then we'll use the ratio to get the moles of chlorate ion, and using moles and volume we can find the concentration of this solution. So first we'll get the total moles which we are using for this experiment. The total moles of iron sulfate original concentration is 0. Uh, the original concentration is 0.075. So 0.075 multiplied by original volume is 150, but that is in cm cube. So we have to convert it to dm cube. That will be 1.12 to 10 power minus 2 mole. That is, these are the moles of iron 2 sulfate which we have originally. Then how many moles are reacted with KMnO4? So first we'll get the moles of KMnO4. It's of 6 marks, so it needs steps. Moles of KMnO4. The mean titer was 9.25, or the titer divided by 1000 multiplied by concentration 0.05. So we'll get the moles, which is 4.625 into 10 power minus 4. But the ratio between manganate and iron 2 is 1 is to 5. So if we have 4.65 into 10 power minus 4, then this will be x. So this will give us the moles of iron 2 which does not react with chlorate ion. That x will be 2.3 into 10 power minus 3. These are the moles. Then how to know how many moles have reacted? So subtract the original one, 1.2 into 10 power minus 2 minus 2.3 into 10 power minus 3. That will give the moles of iron which are reacted, which is 8.9 into 10 power minus 3. And then the ratio between the iron 2 and the chlorate ion is 1 is to 6. So if we have the moles of iron 2 ion, which is 8.9 into 10 to the power minus 3, we will get moles of chlorate ion. So when we use this value, this is the moles of chlorate ion, moles of iron 2 ion. So we'll get the moles of chlorate ion, which will be 1.48 into 10 to the power minus 3. These are the moles of the chlorate ion, but we need concentration. Concentration is moles by volume. So 1.48 into 10 to the power minus 3 divided by volume of that 50 cm3 was there. So 0.05 will get the concentration 2.9 into 10 to the power minus 2 moles per pm3. Explain the change, if any, to the value calculated if the chloride ions are not removed before the step 3. Look, if chloride ions are not removed, this Mn manganate ion is oxidizing iron 2. If there was chloride ions in the solution, that will also be oxidized to chlorine. So means the amount of manganate which is needed will be higher because the manganate ion are oxidizing chloride ion into chlorine molecule. So the value which we of manganate ion will appear to be higher than what we have calculated. Azo such as organol brown can be made by benzene C6H6 using the reaction. Due to toxicity of benzene, first step is never carried out in school lab. Benzene to nitrobenzene. In a preparation, benzene is added slowly in a mixture of concentrated nitric acid and sulfuric acid. The mixture is warmed at 55 under reflux. The reaction mixture is stirred. State why a reflux condenser is needed when the mixture is warm. Why we want a reflux condenser? We want a thoroughly mixing of the reactant. We want the complete reaction. That's why we use a reflux condenser, or we don't want the toxic this benzene to escape. Draw a level diagram. So for a reflux condenser, you should have a condenser in a vertical position. Then in a round bottom flask, you are heating a mixture. It should be labeled. Suggest why reaction mixture is stirred continuously. Basically, what happened, because these are immiscible substances like acids, aqueous acids, and benzene. They don't have the same type of force, so these are immiscible liquids. So when they are immiscible liquid, we have to stir them continuously. So to make sure that they are completely in contact with each other, as they are immiscible liquid due to different types of intermolecular forces. Identify suitable drying agent. As a drying agent, we can use, as you have studied in AS chemistry unit 3, we can use anhydrous sodium sulfate as a drying agent. Nitrobenzene is then reduced to phenylamine. Phenylamine react with nitrous acid in at temperature between 0 and 10. Between why not less than 0? Because the reaction will be slower. And why not more than 10? Because the compound, these azo compounds, these are they are not stable. That is why it might decompose above 10 degree. Nitrous acid is formed in a reaction mixture using sodium nitrite and hydrochloric acid. Suggest why nitrous acid is generated instead of being obtained from chemical suppliers. Nitrous acid is not a stable compound, it can also decompose. That's why it is not, it is just prepared in the reaction rather than used from the chemical suppliers. Explain why the temperature, the same thing, why it is not below 0. The reaction will be very slow, and higher 0, then these compounds are not stable compound. These diazonium compounds can decompose, can react with water, or hydrolysis can occur. Reaction of disonium compound with alkaline solution naphthalene 1-ol produces solid azodine organol. A solid is purified by recrystallization. So these are the steps of recrystallization. Impure organol is dissolved in minimum volume of hot solvent. Why we use minimum volume? To make sure that when we recrystallize, maximum amount will crystallize. That's why minimum solvent. Like if we use too much solvent, then what happens when we carry out a recrystallization? Most of the organol brown will remain in the solution and very small amount will be recrystallized. That's why we use a minimum volume of solution or solvent. A solution is filtered through a hot preheated funnel. Why we use a preheated funnel? To make sure that there is no crystals formed or no crystallization occur for these azodi on the funnel. As they are heated, higher temperature, the solubility is higher, so it will not form solid. And the solution is cooled and filtered using a Buchnell funnel. When we cool down, so Buchnell funnel, it will be fast filtration as well as dry solid obtained. The solid is rinsed with a small amount of ice cold solvent. What is the reason why we are rinsing with ice cold solvent? To make sure to remove the soluble impurities, and the solid is dried in desiccator. Why not in oven? Because the solid might decompose. So state why a minimum volume of hot solvent is used in step 1. Why we use a small quantity of hot solvent? To make sure that all of this, like to make a saturated solution when it will be cooled, or if it was not, like a small volume of a solvent is there, otherwise most of the azodi will remain in the solution when we cool down. So we don't want the acid. So lot of azodi will remain in does not remain in solution when we cool down. That's why we are using a minimum solvent. Why a preheated funnel is there? As I mentioned, why there is a preheated funnel? To make sure that there is no crystallization happen for azodi on the funnel. It will pass through the filter paper with the solution, the solvent filtrate as a filtrate. Give a reason for each of the two filtration step. Give a reason for each of the two filtration step 2 and 3. Step 2, why Buchnell funnel, and then step 3. So in step 2, what is the purpose step 2? Because we want to remove insoluble impurities. And step 3, we want to remove the soluble impurities. That is why we are washing it with. Step 2, a solution is filtered through hot. So that is to remove insoluble. And then the solution is cooled and filtered using a Buchnell funnel. So when we cool down, because when we cool down, the soluble impurities will be crystallized and then they will left on the filter paper. So step 2 is for removing insoluble impurities, and step 3 is to remove soluble impurities. Give a possible reason why it is preferred to dry a solid in desiccator, because this solid might decompose. And then the melting temperature of recrystallized organol brown is measured to check instead what you would observe if the sample is pure. If sample is pure, then it will have a sharp melting point. So this was Unit 6 from January 2021, IEL.